Greetings to you all. My name is Atukunda, and I am presenting a fuzzy patient matching algorithm based on HIV/AIDS patient identifiers in Kampala, Uganda. This work was done by myself, Atukunda, Associate Professor Peter Waitwa, and Dr. Peter Faholi. For effective HIV care and treatment, it is always important to keep accurate patient information from every hospital visit, including information to do with transfer in and transfer out. So we know that most cases, patients move from one health facility to another for different reasons. You find a patient who has been obtaining care and treatment from health facility A has sent to health facility B. And so the patient history at health facility A and the clinician at health facility B do not have access to patient history at health facility A. And health facility A reports a loss to follow-up, while health facility B reports a new enrollment. So such reports have led to increased duplicates. They have led to erroneous loss to follow-up and new enrollment. And several studies indicate that loss to follow-up rates in Kampala district and Wakiso district are at 9% and 20% respectively. And despite over 60 health facilities in Uganda having open MRS, which is open medical record system, the system has unique identifiers which are specific for each health facility, and none of these unique identifiers cuts across all of them. Open MRS is a medical record system that is used for capturing patient records in the HIV care setting. So this leaves clinicians with limited or no access to patient history, yet it is very important for proper patient management. So in the absence of such unique identifiers, fuzzy matching can be obtained. Fuzzy matching provides an improved ability to find matching phrases or sentences from a database when you cannot find an exact match which should have been provided by universally unique identifiers. It attempts to find a match which, although it may not be 100%, it has to be above a certain threshold percentage, which has to be set by the application that one is using. So using the fuzzy patient matching algorithm to match patient records across different health facilities in the absence of universally unique identifiers could actually help reduce duplicates in patient records. It could reduce erroneous loss to follow-up and new enrollment. Our research objectives were: one, to identify suitable parameters and determine how they can be used for patient matching. Two, were to explore data cleaning techniques, then to design a fuzzy patient matching algorithm and to implement and test this algorithm in matching patient records across different health facilities that are implementing Uganda EMR. Uganda EMR is the Uganda National Medical Record System, which is based on open MRS system. So we conducted a desk review of the open MRS concept dictionary to be able to understand the variables that are actually captured in open MRS system. Then we obtained patient records from 5 health facilities in Kampala, Uganda. And then we went ahead and designed data cleaning algorithms, one for data cleaning and standardization, and the other for filling missing variables in the address section, because from our data sets we noticed that the address section had a lot of missing variables, and yet we actually have the Uganda address reference list. So it is the one that we actually use to fill the missing variables in the address section. So the algorithm will pick the district and the village of the patient, and then check with the Uganda address reference registry to fill the missing variables within that address section. The reason why it fits the district and the village is because there may be many villages with the same name belonging to different districts. So we went ahead and designed a fuzzy patient matching algorithm, which is based on Levenson edit distance. Levenson edit distance is the number of insertions, deletions, and substitutions that are required to transform one string into another. And then we implemented this algorithm in OpenMRS system. We went ahead then and conducted an experimental study using a combination of different patient variables, different weights, and typographical errors. The choice of this experimental study was because we wanted to recommend that the patient variable, the best combination of patient variables that actually performs better and which weights can be used in fuzzy matching. We then used the usefulness, satisfaction, and ease of use questionnaire to evaluate usability of this algorithm. So 3 experiments were conducted, and here we used 15 variable combinations from these from the 14 patient variables, and we named these variable combinations A, B, C, D up to N. So in the 15 variable combinations, only one variable combination had 14 variables, had all the 14 variables, while others had some missing information to reflect the real world scenario. In experiment 1, we did record matching using set 1 of the weight, and in experiment 2, we repeated the same procedure as experiment 1, but this time we used set 2 of the weight. And then in experiment 3, we did record matching using set 2 of the weight with the variable combination A, which had all the patient variables, but this time we were testing a real world scenario where there may be misspelled names of the patient, the addresses, and there may be other typographical errors like we noticed in the phone numbers and the date. So we then evaluated usability and effectiveness of the algorithm. Our independent variables were all patient information as collected from the health facilities, and the dependent variables were a match, a possible match, and a non-match. A match was that record whose overall matching score was above 90%. And a possible match was that record whose overall matching score was between 70 and 89.9%, and that whose overall matching score was less than 70% was a non-match. So the record variables which had a higher contribution to the Levenson distance calculation were given weights that were closer to 1, and those with a less contribution were given weights that were closer to 0. This was chosen because there were other studies that had similar studies as this that had used the same. So from the table you see on the right side, we have different patient variables, and then the experiments 1, 2, and 3, and the sets of variables that we use for each of the experiments 1 and 2, and then the different typographical errors, the misspelled names, the interchanged names, because we are mindful that the order in which the patient gave their names in the previous visit to the hospital may not be the same order in which they are giving their names. So we consider the interchanged names, the special characters like hyphens, backslash, and forward slash in the birth date and phone numbers. And then this is the distance calculation that the algorithm uses, and the distance is 1 minus the square root of 1 minus Levenson ratio of I1 times the weight of I1 squared plus the Levenson plus 1 minus the Levenson ratio of I2 times W2 squared until you get all the 14. Then divided by 14, which is the number of variables, times 100. Levenson ratio is a modulus of A and B, where modulus of A and B is the length of strings A and B minus the Levenson of variable A, of variable 1 to the variable 14 divided by the length of string A plus the length of string B. So from the search engine interface, the user enters patient variables, and then they are directed to the OpenMRS server, which returns for them a result. So a result is checked whether it is a match, and then if it is a match, then the user obtains further patient details in OpenMRS, and if it is not a match, it may be a possible match, and so the user can also go ahead and obtain patient variables in OpenMRS. But the result may also be a non-match, indicating that this is a new patient and the details can be now entered into OpenMRS. But there's also a scenario where the patient may have a match and a possible match, and so the user goes ahead and checks both of them, and then is able to check which of the two is the most recent to inform their decision for prescription, for diagnosis, and for prognosis. So what you see there are the screenshots obtained from the algorithm, and the one on the left is where you input the patient variables, and then it takes you to OpenMRS, where it then gives you the percentage of match, and then you can, if the patient has a possible match, it can also be indicated. So the results, we have for the patient variables were name, address, birth date, gender, and then the patient's telephone number, the treatment supporter telephone number, which is also the next of kin telephone number, the first encounter date, which is the date when the patient first tested positive, the at-start date, when this is the date when the patient was enrolled in care. And then the data cleaning algorithms achieved precision and recall of 100%. And this was because the issues that we are dealing with in our data sets were known abbreviations that the system could easily, the algorithm could easily fill, and then the hyphen, spaces, forward and backslashes in phone numbers, and this was easy for the system to handle, giving that precision and recall of 100%. Then accuracy of the data cleaning and standardization algorithm was 98%, while the filling missing variables algorithm was 90%. The difference of 10% in the filling missing variables algorithm came at a point where if the patient reported their village name, and then according to the Uganda Address Reference Registry, it is not a village name, it's a parish name, then the algorithm could not fill the missing variable because it knows that village name as a parish name. So that accounted for the 10%. So in experiment 1, the fuzzy patient matching algorithm achieved a precision recall and F score of 100% for variable combination A, B, D, G, I, and N, and a precision below 100%, a recall below 67%, and an F score that was below 30 for the variable combination C, F, H, J, K, L, and M. In experiment 2, the algorithm achieved a precision recall and F score of 100% for variable combinations A, B, D, G, I, and N, and precision which was below 100%, recall which was below 51%, and an F score which was below 29% for variable combinations C, F, H, J, K, L, and N and M. So we observed that in experiments 1 and 2, the set 2 of the weights performed better in both experiments. And then we went ahead in experiment 3 and used that set 2 that had performed better in experiment 1 and 2, and it gave us a precision of 96.9, recall of 86.1, and an F score of 91.8%. So what you see there is a chart that shows the results from the different experiments. On the y-axis, we have precision, recall, and F score, and then the variable combinations which are on the x-axis. And then you can see the variable combinations for A, B, up to N as seen in the slide. And then we used we ran a critical worry test in SATA, and it showed that there were no statistically significant differences in the mean scores for usefulness, ease of use, ease of learning, and satisfaction, and showing p-value above 0.05. And the users that we did this evaluation from with were clinicians, the data managers, and data officers, and they were 22 in number. The significance of this study, the FPM algorithm, or the fuzzy patient matching algorithm, is very cost effective because it is based on patient identifiers which are already being captured at the health facility. And it can be used in cases where the universally unique identifiers like fingerprint and national ID cannot be used. These are cases where the national ID may not be there, or the fingerprint has failed to work either due to technological issues or the initial enrollment was not done correctly, and this means that the subsequent visits for the patient in the hospital, the fingerprint may not always match. And also patients with fingerprint amputations are always catered for by the FPM algorithm. So the algorithm also provides an advantage that even when the match is not found, other possible matches can be obtained if they are there. So from the experiment, we realized that variable combinations that performed better had less missing variables, meaning the more variables used in fuzzy matching, the higher the precision, recall, and F score. And the two data cleaning algorithms can also be used by the OpenMRS users to clean patient records. And So the FPM algorithm can be used to not only get the best fuzzy match, but other possible matches if they exist in the patient report. And therefore, we recommend that as Minister of Health in Uganda plans the rollout of a national ID and fingerprint identification for patient matching, in cases where these fail to work, fuzzy patient matching can be used. Thank you so much for listening.